Formation of the ions in water. So we're going to talk about how ions form and how they can be found in water samples, and that in turn, how that can impact you. So let's first discuss the fact that metals dissolving in water sounds like a really odd thing. Metals are solids. If you put a piece of copper in water, you don't expect it to break apart into something that can dissolve, right? It doesn't make any sense. So how do you find ions in water to begin with? Well, it turns out what happens is that metals can collide with nonmetals. Now, if you remember back to electronegativity, you remember the nonmetals are very electronegative. That means they attract electrons. And metals have very low electronegativity. So when those two collide, the nonmetal has a strong enough pull of electrons that it pulls the metal's electron away from it. And when it does that, the metal becomes an ion. The nonmetal also becomes an ion, but they're two different types. If you remember, when metals lose electrons, they become cations. The T kind of like a plus sign, which represents their charge, right? Cations, positive. And then when you gain, and let's just talk about that real quick. So cations are positively charged, and they're metals typically. So easy to remember it, the charge and the cations is that the plus sign can look like a T, so cations are positive. And the nonmetal would gain a negative charge because it's gaining more electrons. So ions are soluble in water with positive ions like metal. Cations attract to negative ions. End of oxygen, which is in water. So let's see what that looks like exactly. So when you have water molecules, we'll draw one up real quick. Water looks like this. Water also has electronegativity. There's a positive end and a negative end. The negative end is the oxygen because it's more electronegative. So we're going to put a little negative sign to represent that just so we can recognize it. The hydrogen end is positive. We're going to put a little plus sign next to it so we can recognize it. So what happens is that when you have cations, which are positively charged, like let's say Ca2+, they are attracted to the oxygen end of water. So when water dissolves, when metals dissolve in water, metal ions, the way they do it, the oxygen end is attracted to the cations. And let's say you have a negative ion, let's say Cl-, for example. The negative end of oxygen won't attract it. It'll be the hydrogen end, the positive end. So the way this would look is like this. Here's your negative and here's your plus. So the way the water molecule organizes itself around the ions is like this. The negative end, which is the oxygen, is surrounding the cations, and then the positive end, which is the hydrogens, are surrounding the chloride ions. It's a thing called solvation. This is how they dissolve in water, how ions dissolve in water. Here's another example of that. You can see, once again, the positive ions on this side. Sodium. You can see the sodium molecule, or sodium ion, I should say. See how there's the negative end? The bigger molecules are always the anions. That's how you get this is oxygen. For those looking at it like, how can you tell what's the O and what's the H's? Well, first off, there's two H's for everyone else. That's one way. The other way, the anions are always bigger. So you can see the way it surrounds itself around the ions is that the negative end, which is the O, surrounds the cations, and the positive end surrounds the chloride ions. And that's how dissolving occurs. When you have something like salt, which is a metal and a nonmetal, when you put it in water, they dissolve. And the way they dissolve is that you have the positive ends taking away the chloride and the negative ends pulling away the sodium. All right, the next one we're going to talk about is the octet rule. So it turns out that every element wants to have 8. There's some exceptions. Helium only wants 2, along with the elements 1 through 4, 5 the most, boron, which are content with having just 2 outer electrons, 2 electrons in our last shell. Anything beyond that actually wants to have 8. It's called the octet rule. So let's take a look at metals. The way metals typically form an octet, they lose electrons. So in the case of, let's say, magnesium, this is the way magnesium looks. So you have the nucleus, right? You have the first ring, which has 2 electrons. You have the next ring, which has another 8 electrons. And you have one more ring that has 2 more electrons. So the way a metal like magnesium or any metal really forms ions is that it loses the whole ring. So in the case of magnesium, it loses its whole 2 electrons. Now as a result, it has 8 plus 2, 10 electrons. And that's what makes it a positive charge because it still has 12 protons. And that's 10 electrons, so your charge is positive 2. So for metals, they lose a whole shell. That's why they're so much smaller. If you remember back when we were talking about ion formation, it's also the reason that you get a complete shell, because what happens now that this last ring is gone, they only had 2. The last shell now is this one that has 8. So now if you look at a magnesium, its outermost valence shell has 8 valence electrons, which is what you want as a complete shell. That's how it's able to accomplish it. They become positively charged. Here's some examples. So you need to know group 1A is positive 1, group 2A is positive 2, and group 3A is positive 3. For those wondering, how do I get those charges? That's how many valence electrons it has. So in the case of group 1A, it has 1 valence electron, so it loses 1. That's why it's positive 1. Group 2A is positive 2. Group 3A is positive 3. And that's how you figure them out. So moving on now, checking out the other variations. So here's magnesium again. This is the reason it gets a positive 2 charge. Remember, it has 12 protons, and we talked about it lost 2 electrons, and now its outermost ring has 8 electrons. That's how I got its octet. And if you want to see the math, you can see what it was before. 0 charge, equal protons and electrons, and now it's a positive 2 because it lost 2 electrons. Characters of cations. Group 1A elements are positive 1. Group 2A is positive 2. Group 3A is positive 3. And this is always the case. So you can just memorize these. That's always going to be the scenario. Transition metals can have multiple charges, which means that we need to represent their charge with Roman numerals. So for example, iron 2 is positive 2 charge, iron 3 is positive 3. So in case you don't know your Roman numerals, I represents positive 1, because these are only going to apply to metals. So that's what we can assume it's always positive 1. You're not going to see Roman numerals with nonmetals ever. 2 represents positive 2. 3 represents positive 3. 4 is IV. That's positive 4. V is positive 5. And 6 is VI. So you need to memorize those. You need to know your Roman numerals, because when I give you a Roman numeral, now you can figure out the charge. Makes it a lot easier. Here's some examples of it. So you can see chromium 2, chromium 3, positive 2, positive 3. So for the transition metals, you don't need to memorize their charges. They can be shown to you based on the Roman numeral. But you just need to know what the Roman numeral represents. So that's all you need to do. Here's the periodic table. You can see group 1 is positive 1, positive 2. We're going to skip the transition metals. Group 3A is positive 3. Group 4A, you can see there's variability. So that's why we don't have set charges for it. You can also see variability within group 6B, 7B. You don't have to memorize all these charges because Roman numerals will be given to you, so you don't have to memorize it. Now, there is one exception. You need to know that zinc is always a positive 2, silver is always a positive 1, and T is always a positive 2. For these, there are no Roman numerals, so you're expected to know. Easy way to remember it, Zach. So those have the set charges, just like group 1A is always positive 1. These also have these specific charges, so make sure you memorize that. For the nonmetals, the way it works is that nitrogen's group needs 3 more to get an octet. That's why it's negative 3. Oxygen group needs 2 more. That's why it's a negative 2 to get an octet. And fluoride group needs 1 more. So if you want to look in terms of electron configuration for nitrogen, remember it's this. And remember, for noble gases, you need 2p6, right? So how does it get to that 2p6? Gains 3 electrons. That's why it's a negative 3. Same with phosphide. So that's another set you have to memorize. You need to know 1 is positive 1, 2 is positive 2. You need to know what Zach is. Nitride is negative 3. Oxygen is negative 2. That whole family, and chloride and fluoride and all of them, are going to be a negative 1 always. All right, so continuing on. So negative ions have higher electronegativities than metals. So when they collide, they take an electron. That's why they get negatively charged. And remember, as a result of gaining these electrons, they get an octet. The metals, as a result of losing electrons, get an octet. So everybody's happy. They have a negative charge, and they're called anions for the negatively charged ones from the nonmetals. Here's how chloride looks before and after. You see it's 0. Gain 1 electron, it's negative 1. Remember, it's group 7A. It needs 1 more to get an octet, so it's going to be negative 1. And then you can see what the result is. Characteristics of anions, group 15 is negative 3. Group 16 is negative 2. And 17 is negative 1. Yes, you have to memorize it. There's no way around that, unfortunately. Once again, you can see the charges. Remember, transition metals are variable, but you need to memorize 1, 2, 3, -3, -2, -1. We don't care about this one. We're not going to make you memorize that. All right, Ionic charges from group numbers. Group 1A is +1, 2A is +2. Those are the metals that have set charges that never change. For the non-metals, if you're studying proms, just take the group number, subtract 8. That's how you get your charges. So group 5A is 5 - 8, group 6A is 6 - 8, and group 7A is 7 - 8. That's another way of doing it. So taking a look at it again, lithium has 1 valence electron. So what does it do? Loses it. And now it has a duet, a complete shell with 2 electrons, and now it's happy because it's like helium. Beryllium has 2 valence electrons. So what does it do? Loses both of them, because now it has a duet as well. It has 2 valence electrons in the outermost shell. It's complete. It's happy, because the second ring only holds 2. Group 3A, which should be boron's group, loses 3. So it's +3. Carbon, we're not going to talk about. Technically, it could be 4. Gain or lose 4. Nitrogen, notice it has 5 in the last ring. How many does it want? 8. So what does it do? Gain 3. Oxygen gains 2. And you can see fluoride needs 1 more, and then it's happy. That's what it does, -1. So that's how you get the charges for them. And noble gases have no charge because they already have an octet. So all those in that last group 8A have 0 charge. They never get a charge. And you can see sodium's same thing as group 1A. So guess what it does? It loses 1, and now it has a complete shell. All right, the other thing you need to memorize is the polyatomic ions. These are compounds with charges. So rather than being a single element, they're a whole compound with a charge. The problem here is that the only way to recognize them is to memorize them. So you notice that they're 2 different elements. They typically have O involved, not always, and they have a charge. So you need to memorize that phosphate is PO4, -3, SO4 is -2, NH4 is +1, and these are all the ones you need to memorize. These are the most common ones. There's no way around this. So if I tell you ammonium, you're supposed to know that's NH4 +1 charge. If I tell you thiocyanate, you'd be like, oh, SCN -1. Or if I tell you salt,